on to our main event. We're looking forward to hearing from Bob Miller, and he promised no math. I don't know if that's like, I think he's just trying to scare you. Anyway, Bob's background is in signal and image processing, and he worked for many years at the Grass Valley Group designing switchers and video compression algorithms. He recently retired from designing thermal night vision scopes for Trijicon. Right. And there's a lot more in his background. You might want to talk to him about all that stuff. And his topic tonight is about general relativity, especially as it applies to black holes. Or maybe it's black holes as it applies to general relativity. Which one is it? The both? Okay. Anyway, let's welcome Bob.
This has been a real fun study. I just have loved general relativity in general and black holes in particular. Gravity used to be simple. It was a force. And although historically many didn't like that it's a force that acted at a distance without physical contact, we can at least feel forces. If you ever played with magnets, you know what I mean. You can feel the push and the pull when you bring two magnets together. And therefore, we understand at a very primal level how something that felt like that could cause things to move. Then Albert Einstein said, gravity is not a force. Instead, it's a curvature of space and of time. Nothing there to feel. There's no gut connect between curvature and things moving. And even scientists who write books on general relativity have great difficulty letting go of that feeling that gravity must act like a force, really. It doesn't. I found that all the wrong conclusions that people have about black holes, and there are many, invariably can be traced back to thinking of gravity like it's a force. This evening, I'm going to be talking about black holes. But for you to understand a black hole, you first need to understand a little bit about gravity. And that means curvature, and a little about the equations that govern it. These are two very famous equations. They describe the curvature of space and of time. They use the same word, curvature, but they don't mean the same thing. The first is the Schwarzschild equation. That describes the space around round spherically symmetric objects like the moon, the sun, planets, neutron stars, and especially black holes. The second equation is the Friedmann-Lemaitre-Robertson-Walker equation. It describes the curvature of the big, large-scale universe. Although they both use the word curvature, they don't mean the same thing. We're not going to talk about the second equation, except to say that it's important not to confuse things you've heard about the curvature of the universe with what we're going to talk about tonight. Anything that has to do with a flat, positive, or negatively curved universe, anything that has to do with dark energy, the Hubble constant, the lambda cold dark matter model of the universe, or the Big Bang, all have to do with that second equation. So some of the things I will say may sound very different than what you've heard if you've mostly studied the curvature of the universe, as astronomers tend to do. So keep them separate. So what does that first equation have to do with flat space and curved space? And what is curved space anyway? Well, let's cut a thin slice of space and represent it with a piece of paper. Here is a flat piece of paper. This is also a flat piece of paper. And this too is a flat piece of paper. In what way are all these surfaces flat? They're all intrinsically flat. The circumference of circles drawn on them, if I drew one, would be 2 times pi times the length of its radius. And if I bend the paper, it doesn't change the number of graphite atoms in the radius, nor the circle. There we go. Okay. Circles, obviously, circumference is 2 pi times the radius, but only if you're in flat space on a flat piece of paper. If you crumple it up, that ratio didn't change. Got the same number of atoms in the radius, which is your ruler. Got the same number of atoms around the circumference. So their ratio doesn't change, and the paper, therefore, is still flat. Conversely, the surface of this globe is not flat, and you can't make it flat, no matter how you bend it or try to flatten it out. Let's draw a longitude line there between the North Pole and the equator and call that our radius. Then we'll draw a circle around the equator and call that our circle. Using the radius, using the equator as our circle and the radius from the North Pole to the equator. Did I say that wrong? Using the equator as a circle, yes. What's the ratio between those two? The distance from the North Pole to the equator is 1/4 of a circle. The distance around the equator is 4/4 of a circle, so the ratio is 4, not 6.28, 2 pi. If the ratio is less than 6.28, we'll say that surface has positive curvature. More than 2.8, we say the surface has negative curvature. And if it's exactly 2 pi, then we can say the surface is flat. That is the definition of space-time curvature and relativity. What does it look like? Here is what the curvature of a thin slice of space passing through the middle of a neutron star would look like if it were actually space that was warped. Pretty cute, huh? You're looking from the bottom up at it. Here's a graph of that curvature. The horizontal axis is the distance from the center of the star, the neutron star, measured in flat space coordinates. It's what you'd measure if the star wasn't there. The red lines mark the star's surface. Can you see the red lines? Okay, it's hard to see from here. The blue line is how much that slice of space would have to be warped out of flatness because of the curvature. So this is just basically a line drawn through the center of that. The slice has to bend relative to flat space because there's more space near a star than there would be if the star weren't there. So let me add the neutron star. This is to scale. And as you can see, the warp is a significant fraction of the star's radius. Even though there's a lot of hoopla regarding the curvature of space-time and general relativity, it's really not space that gets warped. Here's a picture of what's really happening. The distance between adjacent circles represents the radial length of a ruler at that location. Each ruler has the same number of atoms, but the atoms shrink radially so that the bulges that we saw in this one disappear. And those bulges were what actually causes the shape to bend out of shape, or causes the slice to bend out of shape, because there's more length in the center than near the edges. A thin slice of space stays in the equatorial plane of the star. So space doesn't bend up out of the plane. Space doesn't expand, rulers shrink. If you drew a circle, however, and measured the circumference and the radius using these local rulers here, their ratio will not be 2 pi. So it is curved, but it's not externally curved. It's intrinsic curvature. And it's curved on the inside, but externally it stays flat.
Could you consider that almost a compression of the space-time?
Well, it's a compression. It's actually um, length um, contraction, standard relativistic length contraction. So it's curved, but it's curved intrinsically. This is curved both intrinsically and extrinsically. This is just curved intrinsically because the rulers get shorter. If we could paint a slice with visible colors like in these images, and you were to look at the star and that slice through a telescope, it would not look warped. It would look like Saturn's rings, or the beam from this laser level. In general relativity, curvature simply means that the length of rulers and the rate at which clocks tick is not the same everywhere. In areas where rulers are the same length and clocks tick at the same rate, we say that space is flat. If not, we say space is curved. It's just semantics. The word gives really absolutely no insight into what's really happening. It's a shorthand name for time dilation and length contraction. So the Schwarzschild equation isn't so much about space and time, it's about using real rulers and real clocks to measure space and time. I want to introduce you to us versus them. We are here on the earth, and our earth rulers and our earth clocks are with us. And they are somewhere else, like near a black hole, with their clocks and their rulers. When we measure the distance between two events with our tools, the Schwarzschild equation can tell us what distance they will measure between the same two events using their tools. Let's examine the elements that make up this equation. Okay, so M is the mass of the central object, be it a planet, a star, a black hole, a neutron star, a moon. The farthest right term there, the plus r squared d omega squared, that represents distance in space that's perpendicular to the radius. On a globe, that would be the coordinate that describes horizontal movement along the surface of a globe with no change in radius. Rulers that are pointed in that direction that are horizontal don't change their length when they get near a massive object. You see there's no n in that term of the equation. So let's get rid of it. This equation is getting simpler and simpler. Okay, r is the distance we measure from them to the center of mass m. So remember, we are on the Earth with our tools. They are maybe near a black hole with their rulers and their clock. dr represents a tiny incremental change in the radial direction. Think of it like the size of an atom. To determine what distance they are going to measure with their ruler, you need to know how long their ruler is. But the length of their ruler may change depending on their location. In fact, each atom of their ruler may be a different length. So to get the total length of their ruler, you'd need to add together the size of each atom in it. dt is a tiny incremental tick of our clock. To determine how much time they are going to measure between two events with their clock, we need to know the duration each tick of their clock, which again may vary with their location. And you'll need to add together the duration of all their ticks to get the total time on their clock. And finally, ds, actually ds squared, is the interval we will measure between two events at their location. So it's the interval that we measure with our equipment, with our clocks and rulers, but we're measuring events that happen at their location at the black hole. And that interval is the same for everybody in free fall. Even though I'm far away, if I'm in free fall and they're right next to a black star, and they're also in free fall, we'll measure the same interval. It's evident from the equation that the relationship of their ticks to our ticks depends upon their distance from the center of the mass. For example, if they're on the surface of a neutron star and they jump up from the surface, what's the tick ratio between their clock and our clock at the peak of their trajectory? So they're in free fall. So we know that the interval is the same. And they're momentarily at rest, right? At the peak. They're not moving. And a neutron star is about 3 miles in radius. So they're 3 miles from the center of the star. Since they're not moving, dr, their change in radial distance, is 0. And 0 times that whole right term makes that 0. So we can get rid of that. We're only interested in the ratio of our clock to their clock. The change in the radial dimension is 0 for both of us because he's not moving. For a neutron star, that 2m value is about 2.6 miles. And the R value, which we said was 3, is distance from the center of the star. 2.6 divided by 3 is 0.866. So everything in that parenthesis equals 866. The interval that I measure with my instruments at his location is 0.86. Well, part in parentheses 0.866 times dt, which is the change in my time. So our measurement of events at their location is on the left. Their measurement of events at their location, again, at their location, they're not moving, so their change in radius is 0. And their change in time, which we will call d tau, equals the interval, because the intervals are the same everywhere in free fall. Then that minus d tau squared has to equal the 0.866 dt squared. So d tau is their clock rate, the change in their clock. dt is the change in our clock. And if you set those equal, you got to take the square root, get rid of the squares, and the square root of 866 is 0.365. So their clock is running about 0.365 times the rate at which our clock runs. Now, technically, Schwarzschild coordinates, which the dt and the r are distances and times measured with rulers and clocks where r equals infinity, far, far away from the planet, in this case, the neutron star. But those clocks, far away from everything, run within 1 part per billion of the rate at which our clocks here on the Earth run. So you can just say, you can plug Earth time in for dt, you can plug Earth ruler lengths in for the change of r. So that value on the top, what happens if r gets to be 2m? 2m divided by 2m is 1, 1 minus 1 is 0, and you get that the interval, you get 0 times our time is what they're going to measure.
They're frozen in time.
Literally. So RS, that 2m on top, is a special number. We call it the Schwarzschild radius. And for the Earth, it's about the size of a marble. Actually, a small marble is 0.35 inches. The diameter of the Earth, if you squeezed it all the way down to its Schwarzschild radius, it'd be about a ½ inch, a little over ½ inch in diameter. The 2M for a neutron star is about 2.6 miles. And the 2M, or the Schwarzschild radius for the sun, is about 3.8 miles.
So you'd have to really squeeze our sun down to make it below that Schwarzschild radius to turn it into a black hole.
Yeah, there's not really any way to do that unless you add mass. In fact, our sun won't even turn into a neutron star. It'll get stopped as a white dwarf because of the electron degeneracy.
Yeah, Pauli exclusion principle will keep the electrons from crushing it down any farther.
Yes, it will. All right. So there's two things we get out of this. One is that if you are approaching a star or approaching a mass of any type, time is going to slow down. And if you're approaching a star, rulers get shorter. So measured lengths get long. If atoms shrink, then the ruler shrinks, and they'll measure a longer distance between events. And that's called length contraction in relativity. If clocks slow down, they'll measure a shorter time between events, and that's called time dilation. While technically, according to our previous definition we showed of curvature, space is curved, intrinsically curved, but it doesn't give you a lot of insight. I mean, I understood a force because I could feel it with my fingers, and I could say, oh yeah, that will make something accelerate. Gravity was a force. But gravity being curvature, I don't even know why they do it. There was no insight, in my opinion, gained by it. The best way to think about gravity is that it's an area where the rate of clocks is not constant. And it's an area where the length of rulers is not constant. So what is a black hole? These, yes.
So are you saying that on the surface of the Earth, that if you have a ruler that's 1 mile up versus one that's on the Earth, actually the distances are not the same?
That's true. In fact, the GPS positioning. Okay. Greg asked the question, does that mean if you have a ruler a mile up versus a ruler at the surface, are they different lengths? Now, if they're horizontally, no, they're exactly the same length. But if you hold them vertically, one will be slightly shorter than the other. And I mean a rigid ruler. I'm not talking about gravity makes like a spring compress by its own weight, that type of thing. I mean a ruler that would not. In fact, you could take a single atom and say that's our ruler, and a single atom at 1 mile up is bigger than an atom on the surface of the Earth, but only in the radial direction. So it squishes flat. It keeps the same diameter in the horizontal direction.
What's making it accelerate towards the center of the Earth? Or am I jumping the gun?
Uh, okay, I can answer that. Well, I can't because I can surmise why it is. First of all, gravity acts on every individual atom. And we know from experiments in cyclotrons and at CERN that when you speed atoms up, they really do slow down. This is very measurable. And they really do flatten. They start to look like a coin instead of a ball. And they can tell this by the um, it's a parameter that's given in Barnes, and I don't remember what it is. The nuclear cross section changes. So these are very real effects. Our GPS system has to take into account the fact that gravity is making clocks run slower at 20,000 miles where these satellites are orbiting. And it also has to take into account the fact that those satellites are moving. So there's some special relativistic effects in addition to the effects of general relativity. The difference in the clock rate of a GPS satellite and one down on the Earth, I believe about 42 nanoseconds per day is the difference between here on Earth and there. And then there's another 7 nanoseconds or so because it's moving, the special relativistic effects. But these are real effects, nothing you and I care about because we don't care about nanoseconds. But if you're doing really precise stuff, you have to take it into account. Okay, these equations, let me go over here and look real quick. Okay, free fall velocity versus r on the left. Acceleration versus r in the middle. And the fall time from r naught, which is down at the bottom, like 12, to whatever point of r you want to know. Now this is for a black hole. In fact, I set it up for the supermassive black hole at the center of the Milky Way galaxy. And I said, if you took that black hole and you put it where the sun is, the outer surface of that black hole would be about a third or a fourth of Mercury's orbit. It would be that big. The R naught point, the starting point, this, by the way, is a particle falling toward a black hole. It's going to, and the starting point is the orbit of the Earth. So if the Milky Way supermassive black hole were sitting where the sun is, and we're sitting where the Earth is, or rather we let go of a particle and let it fall towards that supermassive black hole, weird things happen. Black holes are a wonderful place to figure out the difference between a force of gravity and what gravity really is, because a force would never do this. So let's look at that first graph. The velocity on the right is where the starting point is. The velocity starts at 0. It immediately goes negative, which means toward the sun or toward the black hole. But when it gets to about 2.5 Schwarzschild radiuses of the black hole, it starts slowing down. And by the time it reaches the event horizon, which is at, on this drawing, it's 1 r sub s. I'm sorry, these distances are given in terms of r sub s. So the Earth would be about 12 Schwarzschild radiuses from that black hole, and the event horizon is at 1. The particle stops. A black hole then is a place where the traditional view of a black hole is it's a place that the gravity is so strong that light cannot escape it. Okay. And anything that fell in it, since light is the limiting velocity in space, will never get out of it. So, and once it's in the black hole, it just keeps going because there's nothing that can stop the fall. And all the mass, in this case of that supermassive black hole in the center of our galaxy, is all crunched down into a point, a singularity. And that dividing line in space, I'll get with you, the dividing line in space between where light can escape and where it can't is called an event horizon, yes.
You said the particle is essentially stopping. Is that from our point of view or the particle's point of view?
Ours, not the particles. R, remember R is, I don't know if you can read it. It's dr divided by dt on the left side of that first graph. I'm sorry, what?
What does the particle see?
The particle is in free fall, and it just thinks everything's fine. It doesn't know that its time is slowing down because everything, its clock is slowing down, but if it were a person, its thoughts are slowing down, everything is slowing down. So
So does it get into the black hole?
that's what we're going to figure out. I told you at the beginning that even people who write books on general relativity have a hard time letting go of this comfortable feeling that gravity is really a force. If these equations are to be believed, and we've got no reason not to believe it, they've been proven down to parts in a billion that these things really do happen. If these equations are to be believed, the particle stops at the event horizon, or it has zero velocity at the event horizon. The second graph here is the acceleration of the particle. Starts out on the right, has a negative acceleration, and then the acceleration starts to get reduced, crosses up to positive acceleration, which is going to slow it down because it was going in the negative direction. And then as it gets closer and closer, the acceleration also goes to zero right at the event horizon.
So it's as though it's stuck on the surface of the event horizon there.
Yes, but there's one more thing, and that is the time to actually fall. That's true. Now, all this time and distance is in our coordinates, our rulers here on Earth, and our clocks here on Earth. The clock that the particle might be, if it was a spaceship, the clock on the spaceship just slows down and slows down. The particles start to get smaller and smaller, And at the event horizon, they have a radial thickness of 0. Their time is 0. Now, that's what relativity says. But quantum physics says, well, wait a minute. You can't know the position and the velocity of a particle to that. There has to be some indeterminacy. It's Heisenberg's uh, uncertainty principle. Yes. If the more you know the location, the less you know about its velocity. And if you establish its velocity is precisely, you're not sure where it is. Momentum, okay, yes. But momentum for this particle it's related to velocity. It's velocity times its mass. Velocity squared is the energy. And energy is related to mass. So it's actually momentum. But given a constant mass, it's related to velocity. Momentum is equal to m times v. So we don't know what happens at the event horizon. But the really important thing is the graph on the right. It doesn't matter what happens at the event horizon because really a particle will never reach the event horizon until an infinite amount of Earth time has passed. And this isn't just something I think, I mean, it's in all the textbooks. They show a graph of here is the length of time the particle experiences, and here is the length of time that we on Earth experience, and the length of time that we experience on the Earth. As you get close to the event horizon, it just skyrockets. My computer didn't have enough precision to make that line go any higher. I wound up with a singularity, which is what you get at the event horizon. And people who write textbooks will tell you, oh, it doesn't matter that it takes an infinite amount of time in these Schwarzschild coordinates to get to the event horizon, because in the particle's proper time, it's a finite amount of time to get there. And that doesn't cut water if it doesn't hold water if at the event horizon time stops for the particle. And we're not really interested in the particle's time. We are interested in our time because 99.9999% of the universe goes on our time or something very close to it. I mean, our time here on the Earth versus far out in space only differs by about 1 part in a billion. It would take 45 years to lose 1 second on a clock on the Earth compared to a clock far, far out in space away from everything else. There's something even more stunning. People that would say, you know, it doesn't really happen that way. Our coordinates are not really valid coordinates when you're talking about getting near the event horizon. We can actually put somebody right up next to that event horizon, and their clock is the same as ours. The rate at which their clock is ticking. If you were to create, or excuse me, make a big shell of mass. Hollow on the inside. Thickness of that shell is about 1 kilometer. And its diameter is, say, 150 parsecs. Really, really big. It's made out of lead. 1 kilometer thick shell of lead at 150 parsecs. The event horizon will be right near the surface, outer surface of that shell. On the inside of the shell, in the space on the inside of the shell, that space is flat. All the contributions from the mass in the shell cancel out. Even if you're right up next to the surface, you've got about 1 kilometer's worth of lead in front of you if you're facing the surface, and it's very close. But you have a whole lot more mass behind you, but it's further away. So they literally cancel out. If you look up a Dyson sphere, the problem with making a Dyson sphere is it's disconnected from the sun that's supposedly in the middle. Dyson sphere, you build a big shell around the sun and you capture all the energy. But it won't stay there. It'll just drift around. It doesn't stay centered at the sun because all the gravity that's symmetrical and above your head cancels out. So if I'm standing on the inner surface of that sphere, that shell, I don't feel any gravity. I'm floating around. I can, you know. If you're standing on the outside of that sphere, you have the full gravitational pull of that whole mass. And gravity, it if you are to take that shell and squeeze it down until it's very small, it doesn't change the gravity of for that guy that used to be standing on the outside of it. When stars pulsate, they don't generate gravitational waves because the gravitational field doesn't change based on the how far away you are from the surface. If you remember those equations, the r term was the distance from the center, not from the surface.
Assuming they pulsate spherically.
Yes, it's spherically symmetrical. But anyway, you got this 1 kilometer shell, thick shell. It can't hold its weight up. It's gonna immediately start collapsing. But the guy on the inside, he's sitting in flat space. So his coordinate system, his rulers are the same length as ours here on Earth. His clocks are running at the same rate as ours here on Earth, but he's inside of that collapsing shell. And if we see the shell stop collapsing, as that first graph says it should, he's going to see the same thing. He has to. He doesn't have, there's no other magic in this. There is just the metric of his rulers and his clock, our rulers and our clock, and they're the same. So it has to stop, except for as the outer surface of that shell gets closer and closer to the event horizon, its time is slowed down, and we have something called the cosmic microwave radiation, which permeates all of space. It's electromagnetic radiation. It's got a temperature of about 2.7 Kelvin. But if your time slows down, that temperature goes up for you. And at a redshift of about 1000, the temperature that the guy on the outer surface is going to see is around 2700 degrees. And a temperature, at a redshift of 2000, it's going to be 5000 degrees. And that outer surface is going to vaporize. And it's going to get left behind. And the rest of it will keep on contracting until until a second event horizon is created based on, you lose some mass that got evaporated. If one atom thick layer, if the outer layer of atoms were to vaporize from that falling shell, the remaining mass is smaller and it has a different event horizon radius. And that event horizon radius is about 1 kilometer further in. So, and then that one's going to evaporate and it's going to continue to go in, getting smaller and smaller, but leaving bits of matter stuck in this dead zone of event horizons. And it'll eventually actually collapse until the headroom inside that shell is gone and it smashes together, and it'll still collapse. But all the time, it's going to leave, that space is not going to be empty. It's going to have little bits of layers like onions left all the way from 150 parsecs out down to next to nothing. So the conventional wisdom that a particle falls through the event horizon and just keeps going and winds up in a singularity can't be right if these equations are right. Now there's one more interesting thought experiment we need to do, and that is what, a metal shell holds together. What if it's a cloud of gas? If I were to look at a very large cloud of gas, it's very cold. It's about 13.8 gigalight years, its radius. And if the density of that cloud is about 5 protons per cubic meter, you're going to have an event horizon out at the outer limit of that cloud. And it will start out, this is a uniform cloud, okay? Same density out at the periphery as there is in the middle. But everything's going to start falling in. It'll take a while. After about 23 billion years, you will still have matter scattered all the way from out there to the middle. The middle doesn't collapse very fast at all because there's not much gravity there. It's the mass below your feet that matters, not the mass on the outside. So although it started out uniform, it doesn't end up uniform. It's slightly less dense at the periphery and much more dense at the center. Now that scale is on the order of our universe. So if I were near the center of that cloud of gas and I looked out, what would I see? I would first of all see that, wow, the further I look, the more redshifted everything is because of time dilation at the periphery. And um, and because in many billions of years, stars could form near the center, because you've got the longest time there, whereas out at the periphery, very little time has passed. Stars form, makes things hot. That radiation goes out, uh, propagates outward toward the periphery, and at about a redshift of 1,000, it's going to be, well, in fact, if the temperature in the inner portion was only 2.7 degrees, it's going to be 2,700 degrees at a redshift of 1,000. And your redshift's going to go all the way to infinity at the event horizon. So two things that we think of as hallmarks of the Big Bang Theory: the fact that the further away from us you get, the more redshifted our galaxies. Uh, also happens in a black hole, very big black hole. It will also have a cosmic microwave background because of energy from the center that heats up to a very high temperature objects at about redshift 1,000. Now, there are some different, I'm not saying that we live in a black hole, because the Big Bang is not like a black hole. The Big Bang theory says that galaxies are literally flying apart from each other. And in this model of a black hole, they're not flying apart. So it's very different. Um, Galaxies, uh, the difference between space here and space far away in the Big Bang theory, it's the same. It's based on the fact that the universe is uniform everywhere. Uniform, the uh, density of the universe would not be uniform with a black hole type universe. The question is, can we tell from the center which type of universe we live in? Yes.
The question of center is a little difficult because ideally we're at a four-dimensional universe where time is one of the dimensions, in which case we're kind of more on the shell of a four-dimensional space. So the center is back in time where the thing started as a four-dimensional sphere that expanded out or whatever it is, whatever shape it is. But so it's hard to picture a center in that sense. It's like saying, where's the center of the surface of the Earth in a sense?
There is no center in the Big Bang theory. There is a center in a big gas cloud. Okay. And if you're near the center, it's very hard to tell. Am I at the center of a gas cloud and time is slowing down as I look toward the periphery? Or are all those galaxies moving away from me? It's redshifted either way. There are a couple of differences. And one I've read is, well, one of them is um, light gets extinguished in the Big Bang universe because you have not only the redshift, which causes an extinction of life when you look at it, you also have the universe expanding in 3 dimensions. So the intensity of photons per square inch diminishes as time goes on. Whereas in a Big Bang universe, excuse me, in a black hole universe, you still have the redshift, and you have 1 dimension where photons get spread out. That's the radius. Radially, they um, they reduce the intensity. So Big Bang, there's 4 powers of z minus 1 that reduce the intensity of light from a star. In the big, in a black hole, thank you. I'm getting weary up here. In a black hole universe, there's only 2 powers of redshift that reduce the intensity of starlight. So your luminance distance will look different. The thing is, can we tell that? Because we don't have an absolute distance reference. And we're assuming that it is uh, diminishing at the 4th power, but maybe it's diminishing at the 2nd power. Without a second absolute distance reference, you really don't know.
It's kind of interesting because the James Webb Scope has seen some of these more distant galaxies, and they might be brighter than they actually should be for their redshift. Just recently, I saw an article on that.
Does it have to be one or the other?
Well, it could be anything.
Heck, there may be a whole different explanation that we don't know about, right?
Not really. You mean Big Bang and
Could we be a simulation? I mean, it's hard. So there's lots of possibilities.
yeah, I mean the theory behind the Big Bang is that the universe is uniform everywhere. The density is the same. Rulers are the same everywhere in the universe as long as you're not close to a planet. Clocks run at the same speed uh, throughout the universe. In a black hole universe, that's not true. Uh, and so I don't think there's any way to reconcile them and say that they could be the same. They look the same, but they aren't the same.
We have the dark energy theory, which says that dark energy is making the galaxies in the universe accelerate as they expand outward, at least for the second half of the universe. So how does that translate into this?
Okay, the redshift in a black hole universe is totally determined by the density profile from the periphery to the center. The density of matter. Okay. Now, if you started with a uniform universe and just let stuff fall, you're never going to get a density profile that matches the Hubble constant redshift profile that we have. But there is a density profile that you can exactly match what we see when we look out at the universe. It's very cuspy. Okay, it's not very dense on the outside. It steepens up and gets very dense at the center. It,
Which you would expect in case of attractive gravity, right?
well, it's very simple.
The periphery is to be less dense because
It's
well, in
very,
that case, they're all moving inward.
yes. And it's very like what you get, the cuspy type of mass distributions you get with dark matter, cold dark matter. When cold dark matter collapses, it's a very cuspy thing. Um, so, uh, so any other questions? Yes.
So I'm trying to understand the difference between the Big Bang theory and the black hole theory. And it's always seemed to me, I've sort of enjoyed saying, there's really no such thing as a Big Bang. Based on your math here, I would call it an infinite whimper.
Well,
And it just, as you go back in time, and as you look closer, look, if there's an expanding universe, it's expanding, the rate of expansion is increasing. As you go back into this theoretical center, you never get there. So there was no Big Bang. It goes back infinitely in time.
And the time was just
if when Einstein first came up with trying to find a universal solution for his equations, um, he threw something in there called the cosmological constant because he realized that, hey, if I have a universe full of matter and it's all very uniform, if I take a little section of that, uh, any section, it doesn't matter, everything outside of that, uh, I'm not going to feel uh, because it's just like a shell. It all cancels out. So the mass that's inside that imaginary circle I draw is only going to feel itself and it's going to collapse. It has to collapse. So the universe as a whole has to collapse. And he says, well, what if there's this cosmological constant that's kind of like anti-gravity? It counteracts a pull. Yes, dark energy. It and so that's a very potentially real thing because today they believe there's, I believe it's what 0.3% of the energy in the universe is dark energy. Uh, uh, Speeding up the collapse, or I forget. Yeah, speeding up the expansion, reducing the. Um, so, tell me your question one more time.
Well, based on your equation, if you apply that
Oh,
to
okay.
the Big Bang, then there's not a Big Bang. It's an infinite whimper.
The difference is if the universe is expanding, you take any small section of it and you can ignore the rest of the universe, just concentrate on that. That causes a certain gravitational collapse. But there's an escape velocity. There's a certain amount of matter inside that region. And if things are shooting outwards faster than the escape velocity of the matter inside of it, it'll expand forever. It'll go forever. The um, satellites that we shot off, that Voyager satellites, they're past the escape velocity of our sun, and they're just going to keep on going out into interstellar space. So, depending on what the average density of the universe is, if you give it an initial velocity that's greater than the escape velocity, it will expand forever. So, yeah, I mean, we have no idea what could have given uh, the universe that kind of a momentum in its expansion. Uh, it, it's just mind-boggling. And it seems to be precisely the right amount to make the universe flat. So, you know, yes, there could be a Big Bang theory, even in spite of this, if the Big Bang imparted enough energy to the matter at the start to exceed the escape velocity.
Makes a lot more sense than cosmic inflation.
Yeah,
Sounds more like fresh oil.
The trouble with, that they see now, though, is when they look back in time, you see that initially things were slowing down for the first 6 billion years. If you look at using type 1 supernova for distance measurements, and you measure their distance, you see that in the earlier universe, things were expanding, but they were slowing down. And after about 4 or 5 billion years, they started speeding up again. And so we're actually in an acceleration. So we're speeding up the rate of expansion now, is what, at least that's predicting from those measurements.
and in a black hole universe, that just means it's denser. That density totally determines the redshift. And so, you know, you can get any Hubble constant, any change in the Hubble constant with distance that you want by manipulating the density. But it turns out that it's the density profile that reproduces the Hubble constant is not very complicated. It's a second order equation of average matter versus distance. And so I don't know. I mean, I can't definitely say. I can say qualitatively they're the same. Quantitatively, they could be the same given the right density constant. But if extinction of starlight turns out to be the fourth power instead of the second power, then it's Big Bang. There's also, in a Big Bang universe, things are expanding. So as you look further back in time, things get bigger instead of smaller. And that won't happen in a Big Bang universe. But again, we do not have. Right. I'm sorry, it's a Big Bang. Yes. Big Bang, things get bigger as you go. You have to get way out there before you notice that effect. But we don't have an absolute distance scale, so we really don't know whether they are. Yes. Now they have run some experiments. One to find out, is it really the fourth power of Z that, and they came up with somewhere between 2 and 3. And there was error on both, both
So either
directions.
one could be correct.
Yes.
The air brackets on the measurements are so high.
And it had to do with the wavelength of light that they were looking at when they ran this experiment. 2 different wavelengths gave 2 different answers.
Any parting words?
No, it's been fun talking to you and great questions. Thank you so much.
Right. Thank you.